Good morning, friends. This is my next lecture on the topic chemical thermodynamics, and today we are going to discuss the new point from the topic, that is the enthalpy of combustion. So, as far as enthalpy of combustion is concerned, enthalpy of combustion represented by delta C H. It is standard enthalpy of combustion. Standard enthalpy of combustion, delta C H naught. Okay. So as far as standard enthalpy of combustion is concerned, we know enthalpy of reaction or enthalpy of what we call as simply enthalpy of reaction, or enthalpy means what. And as far as standard enthalpy of combustion is concerned, for that purpose, if you consider reaction simply, suppose C2H2 gas plus oxygen gas reacts to form, means it is ethine or acetylene. Okay, when oxidation takes place, when complete oxidation occurs, it results in the formation of carbon dioxide gas plus water. Okay, plus water in the liquid state. Okay, in the liquid state is formed. So for this purpose, for this reaction, the enthalpy of reaction, the delta RH naught, for this reaction delta RH naught is found to be, it is minus 1300 kilojoule, minus 1300 kilojoule. And if you balance this reaction, two carbon atoms are there, twice CO2, oxygen 5, oxygen 2 4 and 1 5, so it is 5 by 2, so it is 5 by 2 oxygen is there, hydrogen 2, hydrogen 2, it is balanced. Now this reaction, if you consider the ethine or acetylene, on complete oxidation gives carbon dioxide and water, and during this course of reaction, the enthalpy which is evolved, or heat energy which is evolved, it is of minus 1300 kilojoule. This much amount of energy is released. Means what it indicates this reaction? This reaction indicates that when when 1 mole of ethine or acetylene, that is the C2H2, when 1 mole of ethine or acetylene on complete oxidation, complete oxidation, after complete oxidation of 1 mole of ethine in its standard state, because it is in gaseous state, so in its standard state, the enthalpy or the energy evolved or enthalpy change occurs, value, that enthalpy change occurs is of minus 1300 kilojoule. So this 1300 kilojoule is nothing but simply enthalpy of combustion. It is enthalpy of combustion. So when it evolves 1300 kilojoule, whenever 1 mole of substance in its standard state, 1 mole of substance in its standard state on complete oxidation, whatever enthalpy change occurs, that enthalpy change we call as simply enthalpy of combustion. So simply enthalpy of combustion is nothing but that is the enthalpy change when 1 mole of substance in its standard state completely oxidized, okay, or burns completely, combusts completely, okay, it forms enthalpy change occurs, that enthalpy is called as an enthalpy of combustion simply. Okay, so this is about overall enthalpy of combustion. Okay, then after that we are going to discuss the next point, that is the bond enthalpy. As far as bond enthalpy is concerned, see here, bond enthalpy. Okay, bond enthalpy. As far as bond enthalpy is concerned, now see here, bond enthalpy. If you consider the simply first reaction, just consider that is the hydrogen gas gives H gas plus hydrogen gas. And in this case, the enthalpy change occurs for this reaction is delta RH naught, standard state. For the removal of the hydrogen molecule मधले 2 hydrogen atoms separate करून जी energy लागणार आहे, सप्लाय करायला लागणार, it is 436 point something, adding 4 kilojoule. This much amount of energy is plus, remember it is positive, isn't it? Okay, means it is an endothermic reaction. So it is bound enthalpy. Bond enthalpy means for hydrogen molecule मधला 1 mole substance, म्हणजे हायड्रोजन मधून हायड्रोजन डॅश हायड्रोजन हा पर्टिक्युलर कोव्हॅलंट बॉन्ड ब्रेक केल्यानंतर त्याच्यापासून करस्पॉन्डिंग ॲटम्स किंवा आयॉन्स तयार होत असताना लागणारी रिक्वायर्ड अमाऊंट ऑफ एनर्जी or heat, that energy or heat we simply called as an bond enthalpy. That energy or heat is simply called as an what we call bond enthalpy. So remember well, here heat energy is not released. Because for the breaking of this bond, energy must be supplied. Means it is endothermic reaction. Isn't it? Delta H is positive one. So what is bond enthalpy? Bond enthalpy is nothing but that is the energy required or heat required for breaking particular covalent bond from one mole of gaseous atom to form corresponding atoms or ions in gaseous state. In also gaseous state one, okay, it is called as bond enthalpy. So for this we can say that for this reaction breaking of hydrogen covalent bond and to form two hydrogen atoms, the bond enthalpy for this reaction is 436.4 kilojoule. Okay, if you consider the chlorine gas to gives chlorine gas plus Cl gas, for this reaction delta RH naught is plus 242.7 kilojoule. What indicates that chlorine madla this particular bond for the breaking the chlorine bond to form two separate chlorine atoms, the energy required is 242.7. Means this 242.7 kilojoule is the bond enthalpy for this chlorine. Remember, it is the bond enthalpy for chlorine. Now one more point, that is the, if you consider actually hydrogen and chlorine which we are considered already here, they are the examples of, that is the monodiatomic molecules. If you consider one heterodiatomic molecules, like suppose HCl, okay, HCl gas, and the bond required, that is the energy required to break the bond between hydrogen and chlorine to separate hydrogen gaseous and chlorine gaseous, the energy required or enthalpy change during that course of the breaking of hydrogen chlorine bond is 431.9 kilojoule. 431.9 kilojoule means what indicates that this much amount of energy is to be supplied to 1 mole of HCl in gaseous state 1. Then and then only hydrogen and chlorine atoms are separated. Okay, because the bond between hydrogen and chlorine is broken by supplying this much amount of energy. So far we are concerned, that is bond enthalpy. If you look carefully, that is the bond enthalpy for monodiatomic molecules, or it may be heterodiatomic molecules. Okay, for monodiatomic molecules and for heterodiatomic molecules, if you observe, means monodiatomic molecules means those molecules which are prepared by a combination of same atoms like hydrogen H-H, chlorine Cl-Cl, O2 oxygen, nitrogen N-N in N triple bond N. So these are the monodiatomic molecules. Heterodiatomic molecules by combination of two different atoms, HCl heterodiatomic molecules, HBr heterodiatomic molecules. Okay, or suppose HI heterodiatomic molecules. Okay, in this way these are the heterodiatomic molecules. If you consider these monodiatomic or heterodiatomic molecules, the bond enthalpy for monodiatomic or heterodiatomic molecules is similar to that of the enthalpy of atomization, delta atomization H. It is similar to that of the enthalpy of atomization. For delta RH naught bond enthalpy, remember well, just I write here, it is the enthalpy of atomization. Enthalpy of atomization is exactly equal to, that is the bond enthalpy only for these two, that is the monodiatomic molecules and heterodiatomic molecules. Because if you look carefully, either in monodiatomic molecules or in heterodiatomic molecules, there is only one and one single covalent bond is present. And for that particular breaking bond, atoms has to be separated. There are two possibilities, two atoms, that is they are separated from each other. So we call it as a enthalpy of atomization or simply bond enthalpy. Both these values are same. Both these values are same one. Now question arises in case of polyatomic molecules. Question arises in case of polyatomic molecules, because as far as polyatomic molecules are concerned, in polyatomic molecules their number of atoms are more than 2. Number of atoms are more than 2 involved in such molecules one, and as number of atoms are present more than 2, in the sense number of covalent bonds or simply bonds which are present also more than 2. Okay, more than 2. But what is bond enthalpy? That is the enthalpy change or energy required to break a particular covalent bond. Covalent bond from that 1 mole of gaseous substance is the bond enthalpy. And what is enthalpy of atomization? Enthalpy of atomization is the energy required to break all the bonds from that molecule. ओके, ज्या मॉलिक्यूलमध्ये सगळे बॉन्ड्स जे पॉसिबल आहेत, सगळे बॉन्ड ब्रेक करून सगळे ॲटम्स एकमेकापासून सेपरेट करणं म्हणजे एन्थाल्पी ऑफ ॲटोमायझेशन. आणि त्या मॉलिक्यूलमधला एकच पर्टिक्युलर कोव्हलंट बॉन्ड ब्रेक करण्यासाठी लागणार एनर्जी म्हणजे इट इज बॉन्ड एन्थाल्पी. सो जस्ट फॉर कन्सिडर मोनोडायटमिक और हेटेरोडायटमिक ओनली सिंगल बॉन्ड आर प्रेजेंट, सो यू कॉल एन्थाल्पी ऑफ ॲटोमायझेशन और बॉन्ड एन्थाल्पी, नो प्रॉब्लेम. But question arises in case of polyatomic molecules. So for polyatomic molecules, the enthalpy of atomization, that is atom H, is not exactly equal to delta R H naught of bond. हे दोन्ही इक्वल होणार नाही. फॉर केस ऑफ polyatomic molecules, these two values are different from each other for polyatomic, but these two values are same for diatomic molecules, maybe monodiatomic or maybe heterodiatomic molecules. Okay, now see, if you consider one example of such polyatomic molecules. Polyatomic molecules मध्ये example जर consider केलं तर the best example is of polyatomic molecule is the water. If you consider water, that is a polyatomic molecules, H2O in gaseous state 1, and if you want to break the what we call as the bonds from the water to separate oxygen and what we call two hydrogen atoms, oxygen and one hydrogen separate करायचं झालं, त्या केसमध्ये हायड्रोजन गॅस प्लस ट्वाइस हायड्रोजन गॅस प्लस ऑक्सिजन गॅस, द डेल्टा आर एच नॉट फॉर दिस रिएक्शन इज 927 किलोजूल प्लस 927 kilojoule plus 927 kilojoule. This much amount of what we call as energy required to break the two oxygen dash hydrogen bonds to separate hydrogen and oxygen from each other. Oxygen and hydrogen from each other. Actually, this is the we call as a what we call enthalpy of atomization. Because from one mole of water, if you consider oxygen, here hydrogen, two bonds are present, and both these bonds are broken, and two hydrogen atoms and one oxygen is separated one. So simply we call as enthalpy of atomization. Enthalpy of atomization. Okay, actually if you consider the water molecule, the nature of both this number 1, you call number 1 and suppose number 2. Number 1 oxygen dihydrogen bond and number 2 oxygen dihydrogen bond, sir, both are similar in what we call as the properties, their bond lengths, what we call as hybridization state of hydrogen with respect to oxygen with respect to number 1 hydrogen, number 2 hydrogen, isn't it? All these bond length and bond angles, bond strength are same. So as bond length, bond angle, bond strength, all the parameters are same, therefore energy required to break first bond and energy required to break second bond, both energies are also required, expected to be same, but this is not. For to break either this or this, okay, which one first break, either this, you consider this bond first or you want consider first one, no problem, because both bonds are what we call as a chemically and identical in nature. So for breaking these two different bonds, the energy required is what we different. So what is, now see, if you consider H2O gaseous state 1, to break the one bond, first bond between hydrogen and oxygen, and separate one hydrogen gaseous plus oxygen dash hydrogen gaseous, enthalpy of reaction for the breaking this particular bond, या केसमध्ये होणारे एन्थॅल्पी चेंज आपण म्हणणार, पण पर्टिक्युलर OH बॉन्ड ब्रेक करण्यासाठी. आणि ह्या केसमध्ये परत राहिलेला OH फर्स्ट रिॲक्शन, दिस वन इज द सेकंड रिॲक्शन, OH गॅस अँड देन लेफ्ट हायड्रोजन गॅस प्लस ऑक्सिजन गॅस, ह्या केसमध्ये होणारी डेल्टा आर एच नॉटची व्हॅल्यू तर चेक केला तर फर्स्ट केसमध्ये पहिला ऑक्सिजन डाय हायड्रोजन बॉन्ड ब्रेक करण्यासाठी लागणारी एनर्जी जी आहे इट इज 499 किलोजूल. ओके, 499 किलोजूल दिस फर्स्ट बॉन्ड ऑक्सिजन हायड्रोजन बॉन्ड ब्रेक करण्यासाठी. आणि सेकंड हायड्रोजन ऑक्सिजन बॉन्ड ब्रेक करण्यासाठी इट इज 428 किलोजूल. ओके, बोथ आर पॉझिटिव्ह. both are positive kilojoule. This much amount of energy is required. Now if you carefully observe, for breaking first oxygen dihydrogen bond, energy required is 499, and for breaking second one, that is the last oxygen dihydrogen bond, the energy required is 428. And if you add these two reactions, हे दोन रिएक्शन जर आपण ॲड केले तर OH आणि हा OH कॅन्सल, OH आणि OH कॅन्सल. सो लेफ्टला जे आहे ते लेफ्टला, राईटला जे आहे ते राईटला जर घेतले तर H2O गॅस कन्वर्ट्स इंटू हायड्रोजन ट्वाइस H गॅस प्लस ऑक्सिजन एक आहे, एक ऑक्सिजन. आणि ह्या केसमध्ये ओव्हरऑल होणारी एन्थॅल्पी ही ॲडिशन, चेंज इज ॲडिशन. सो इट इज 927 kilojoule. This much amount of energy is required. So similar. Okay, here. So actually it is enthalpy of, still I saying it is enthalpy of what we call as enthalpy of atomization. But if you consider the want to write the what is the delta H naught of bond enthalpy of water. जर बॉन्ड एन्थॅल्पी, वॉटरची बॉन्ड एन्थॅल्पी लिहायची असेल तर वॉटरची बॉन्ड एन्थॅल्पीमध्ये पर्टिक्युलर ऑक्सिजन डॅश हायड्रोजन बॉन्ड ब्रेक करण्यासाठी, हा ऑक्सिजन, हा हायड्रोजन आणि हा हायड्रोजन, हा असेल किंवा हा असेल, पर्टिक्युलर एक बॉन्ड ब्रेक करण्यासाठी लागणारी एनर्जी म्हणजे बॉन्ड एन्थॅल्पी. मग कोणती घ्यायची? फर्स्ट केसमधली जर कन्सिडर केली इट इज 499. ओके, सेकंड केसमध्ये कन्सिडर केली 428. सो बोथ दिस टू व्हॅल्यूज आर डिफरंट. So which one we are going to write here? Either 499 or 428. We don't write here 927 because 927 is the what we call as the enthalpy of atomization. That is the all bonds are broken, and for to break all the bonds the energy is 927. So we are not consider 927, either 499 or 428. So and one more point, that is the chemical nature of both these bonds are identical. So in such cases one, this concept can be solved by considering that is the average bond enthalpy. In polyatomic molecules, the concept of bond enthalpy can be solved by taking average bond enthalpy. Very important. So what is average bond enthalpy? Average bond enthalpy is the energy required to break all the bonds, or enthalpy released, or energy required to break all the bonds, that is the enthalpy of reaction, divided by number of bonds present in that molecule. So what is in water? First bond, for to break first bond, energy required is 499, isn't it? So 499 plus for to break second bond, energy required is 428, and total number of bonds present, how many number of total bonds? 2 present, so divide by 2. So this solve, if you solve this one, it comes out to be 463 point, I think it is 5 kilojoule. 463.5 kilojoule. So 463.5 is the bond enthalpy of water. 463.5 is the bond enthalpy of water, which is considered average bond enthalpy, only considered in case of polyatomic molecules. But in case of diatomic molecules, as such, only one single bond is present. To break that particular bond, the bond enthalpy and enthalpy of atomization both are same. But here, remember well, this value indicates the enthalpy of atomization. But this value indicates bond enthalpy. The next, we're going to solve the what we call the problems or examples together of all these types. Okay, so next point is the Hesss law of constant heat summation. Hesss law of constant heat summation. So what is Hesss law of constant heat summation now here? Okay, as far as Hesss law of constant heat summation is concerned. So first, what is Hesss law? Before that, now see here. Consider a reaction, general reaction. Suppose A converts into C. Okay. No, not necessary to write the gaseous state or solid state, liquid state. Just consider A is the reactant converts into C, isn't it? So it is call this reaction number suppose first. We call this reaction number suppose first one. And this one reaction is a direct conversion. It is a direct conversion of reactants into products. Now if you consider the alternatively, if I convert first A into B, and then B converts into C, you call this reaction as a second reaction, and it is final reactant to final product, this is the indirect conversion. This is indirect conversion. Whatever enthalpy change occurs in first case and second case, if you consider, in first case, suppose enthalpy change occurs is suppose delta H1 naught, isn't it? And in second case, for the conversion of A into first B, the enthalpy change occurs, suppose it is delta H2 naught, and in the conversion of B to C, enthalpy change occurs is the delta H3 naught, So for the conversion of A into directly C, delta H1 naught is the enthalpy change. But the same conversion indirectly, A to B, delta H2 naught, and then B to C, delta H3 naught 1. So in this case, we can write indirect conversion, that is delta H1, or suppose we call delta H1 naught. Here suppose delta H4 naught, if I write, because 1, 2 and 3 are covered. So delta H4 naught, if you consider, this delta H4 naught is the delta H2 naught plus delta H3 naught. Delta H2 naught plus delta H3 naught has a conversion overall A to B, B to C. Overall reaction kind of enthalpy change H2 naught plus H3 naught, delta H4 naught. So according to Hess law, delta H1 naught is exactly equal to delta H4 naught. Means what it indicates that? If you convert A directly into C, in direct process 1, the enthalpy change occurs is delta H1. Delta H1. Or if you convert first A to B and then converts this B to C in indirect process. So this is first step, and this overall A to C, it is the second step. So enthalpy change occurs in first step and second step, both are same. This is the what we call as the concept of the Hesss law of constant heat summation. Means when a process carried out in single step, or if the same process is carried out alternatively in the number of steps 1, then the enthalpy change occurring in both these process remains same. म्हणजे आपल्याला इनिशियल स्टेट कडून फायनल स्टेटला जायचं आहे. इफ यू प्रोसीड डायरेक्टली, or if you go like this zigzag manner, or if you go one more like this, in this case one, initial to final. This is the first case, suppose this is second case, this is suppose third case. So in all the cases, one initial state and final state, both are same for all these routes, but just we make difference in the path to reach the final state from initial, direct gear, okay, and indirect. So in all these cases, enthalpy change occurs in first case, second case, and third case. Enthalpy change occurring is the same. And all these cases, enthalpy change occurring in the same. That is the property. Yes, that is a state function. That depends values, which depends only on the state of system, not on the path followed by the system. That's why one of the most important point, that is the enthalpy. Enthalpy is a state function. Is the direct consequence. Means Hesss law of constant heat summation is a direct consequence to explain the enthalpy as a state function. Enthalpy is state function आहे, याचं एक्सप्लेनेशन सुद्धा देतं. There is a Hesss law of constant heat summation. And the examples, that is the particular example त्या केसमध्ये जर मेमोराइज करायचं असेल तर त्यासाठी दिलेले एक्झाम्पल्स जे अमोनिया किंवा वेगळे जे दिलेले आहेत, नॉट नेसेसरी टू मेमोराइज दॅट व्हॅल्यूज, जस्ट वी ऑलरेडी स्टडीड व्हॉट वी कॉल एज व्हॅल्यूज जे आहेत हीट ऑफ सब्लिमेशन, सो एन्थॅल्पी ऑफ सब्लिमेशन, त्याच व्हॅल्यूज इथं कन्सिडर करायच्या. सो एन्थॅल्पी ऑफ सब्लिमेशनमध्ये काय केलं, इट इज H2O. फर्स्ट केसमध्ये H2O इज इन द सॉलिड स्टेट, आईस कन्वर्ट्स इन टू H2O gaseous state. Here delta sub H, enthalpy of sublimation, it is 51.08 kilojoule per mole. 51.08 kilojoule per mole. It is plus. It is plus 51.08 kilojoule per mole. It is the first case. Second case, alternatively, or rather than first and second, it is suppose A and in B step 1, in that B first case, that is the H2O solid first converts into H2O liquid state by the process enthalpy of fusion, delta fuse H, and this value comes out to be plus 6.01 kilojoule per mole. kilojoule per mole. In second case, that is the H2O liquid is converts into H2O gas, and this process is called enthalpy of vaporization. With delta H, this value comes out with plus 45.07 kilojoule per mole, isn't it? So in this case, water in the solid state directly converts into liquid. Just I make here diagram. It is a triangle. H2O solid converts directly into H2O, that is the gaseous, H2O gaseous. It is a single step process, direct process, first step, isn't it? Or H2O first converts into H2O solid converts into liquid state, and from liquid it is converted into gaseous state. So it is the alternatively second step, alternatively second path one. So first path, and this is the second path. So according to Hess law, in both the cases enthalpy change occurring must be same. Just I will explain it here. Now see here. If you add these two reactions, this is direct and this is indirect process. If you add these two indirect process, one, then H2O liquid cancel, H2O solid is converts into H2O gas, and enthalpy of sublimation, solid to liquid, and enthalpy of vaporization, that is liquid to gas, means indirectly solid to gas, that is enthalpy of sublimation. Delta sub H, if you add these two, it comes out with plus 51.08 kilojoule per mole. Actually this value 51.08 and this value 51.08, both are same, and as both are same, in the sense we say that is the whatever change if we occurs in a single step, or if the same change occurs in the number of steps one, the enthalpy change occurring in both the cases remains same. That is the what we call as the basic concept of Hess law of constant heat summation. Hess law of constant heat summation. So this is overall about the Hess law of constant summation. So in next lecture we are going to, I think it is the last lecture of this topic one, because from here onwards the spontaneity, entropy is irreversible concept. This can be omitted for this year. So we are not going to deal that points one. So just one example points, numericals are left on the just 2 lectures behind. We are going to cover that numericals in the next lecture. Okay, hope you understand all these things. Okay. Good day.